SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture 42. We are discussing about the design of low speed axial flow compressor. In last session, we have discussed about different design approaches. So for this numerical, we have solved by using approaches called free vortex concept. We have used fundamental approach. Now today we will be discussing about the force vortex concept. Now this is what is a table, that's what we have made during our week 3. And if you realize, there are different methods which are available for design of axial flow compressors, out of which for this particular numerical we have opted with the free vortex design, and we have opted using work loading or our fundamental method. Now today's lecture we will be focusing on force vortex concept. So for force vortex, we can say our work, that's what will be varying with radius square. Our distribution for work, that's what will be Cw by r equal to constant. We will be calculating our axial velocity based on our radial equilibrium equation. Most important, how my degree of reaction, that's what will be varying, that's what we need to check with. And this is the method, that's what is following our radial equilibrium. And mostly this method, it is rarely been used, but still in order to understand different approaches, it is preferred to go with this also. So you can understand, like we are solving the same numerical using different methods. That's what will be giving us fundamental idea how do we proceed with. So it will take many hours if you will be solving same numerical by using these 7 methods, and that's what will not make much sense. And that's the reason why we have selected these 3, because that's what is most widely been used, and why it is not been used, that is also we need to understand. Okay, so let's move with our next method, that's what is force vortex method. Now here in this case, we know when we are designing our low speed axial flow compressor, for that we are doing all our initial calculation at the mid station. So here if you look at, this is what is my mid station, and that calculation, that axial seat, that's what remains same for free vortex, for fundamental method as well as for force vortex method. So my mean line calculation, that's what will be remain same as we have done for past 2 methods. Now when we say we want to do design for force vortex concept, then we need to realize how do we proceed with. So similar to what all we have discussed for earlier 2 methods, we will be calculating our different velocity components, our velocity triangle, we will be checking with different velocity components. And as we know, here in this case for force vortex concept, my axial velocity, that will not remains constant. That means we need to do the calculation for that. Okay, so at entry and at the exit, we will be calculating different flow parameters. We will be calculating different parameters called degree of reaction, diffusion factor, d'Euler's factor. We will be calculating different flow angles at particular station initially, and then after we will be applying our design law for other stations. Okay, so let's see how do we proceed with. So in order to do the calculation at different stations, here in this case it is given my entry is axial, that means my Cw1 or my whirl component at the entry, it is 0. Okay. Now, in order to solve this design, or in order to do design, we will be assuming my whirl component at the exit, that's what is following B into R, that is CW2 equal to some constant B into radius R. Okay. Since at mid station we know what is our CW2, we know what is our radius. If we will be putting my CW2 at the mid station is 28.48 and my mid radius is 0.15, that's what will be giving me my constant B. It is say 189.87 per second. So we can say now we know what is our constant. Now this method, we need to check the variation of work as force vortex, that's what is not following constant work loading. Okay. So what we can write down from our fundamental approach, we can say my thermodynamic work and aerodynamic work, they both are same. Here in this case, what we know, CW1, that's what is equal to 0, and my CW2, that's what we are putting as a B into R. So you can say my work, that's what is varying with say R square. Okay. Now the work, that's what is varying with the radius, a check for average pressure is required if we are achieving our objective or not. We will see how do we proceed with. Now important parameter, that's what is called say degree of reaction. So if we are putting this degree of reaction, my CW1, that's what is equal to 0, and CW2 we are putting B into R, that's what is saying my degree of reaction is given by 1 minus B by 2 omega. Omega is my angular speed. So we can say my degree of reaction, that's what is independent of radius. Let me tell you, here we have assumed our force vortex by taking CW equal to B into R. So if you recall, when we were discussing different approaches that time, we have discussed about arbitrary selection of whirl component. If that kind of configuration we are having, this degree of reaction may be having some different numbers. Okay. So we need to check carefully. For this kind of configuration, for say CW2 equal to B into R, we say our degree of reaction, that's what is independent of radius, that means that's what remains constant. Okay. Now what we realize is we don't know what is our axial velocity, because we know in order to satisfy the radial equilibrium, we need to have total enthalpy at say throughout my radius or my work distribution, that's what will be remains constant. Second condition, that's what is my axial velocity, that's what is remains constant throughout my span. And third, that's what is CW into R equal to constant. If we are satisfying these three conditions, we can say our radial equilibrium, it is satisfied. And then we have discussed maybe one of the parameter, if we will be putting as a constant, other parameters can be calculated by using this radial equilibrium equation. So that's what we are doing here. So this is what is my fundamental equation. It says dH0 by dr, that's what is equal to Ca into dCa by dr plus Cw by r dCwr by dr. Now here in this case, what we know, my H0, that is nothing but it is say lambda omega b r square, that's what we have calculated earlier. Same way my Cw we are putting, that's what is say B into R. Okay. If we are putting this in this equation, it says we will be getting the formulation in the form of different radiuses. Okay. Now this is what it says in sense of my dC A by dr, that's what is equal to say 2 lambda omega br minus 2b square into r. Now in order to do the calculation for the variation of axial velocity, we will be doing the integration from some location, say our known location, that's what is say Rm, to any radius r. So we can write down this equation in the form of integral form. Okay, so this is what is nothing but this is what is giving me integral form. Now if we are solving that, we will be getting, say, ratio of my axial velocity at any radius divided by my axial velocity at the mid station. That's what is given by this formula. So again you can check with the module 3 where we have discussed about different design methodology. In that also we have discussed how do we calculate our axial velocity. That's what will be giving you the idea. So now here in this case we understand, say, my axial velocity at particular station, that's what is varying by this formula. So let's calculate at, say, hub station. So we can say at hub we will be putting this number. It says at hub my axial velocity is coming 32.83. We can understand at mid station we are having our axial velocity, that's what is 36.69. Okay. Now what is happening at the tip? So if we are putting these numbers, since we know what is our B, what is our axial velocity at the mid station, different radiuses, mid radius, that's what will be giving me my axial velocity at the tip, that's what is 41.49 meter per second. So we can say near the hub our axial velocity is lower, near the tip region our axial velocity is coming to be higher. Now this is what is somewhat different compared to what all we have done for our fundamental method as well as what we have done for our free vortex method. For that we have assumed our axial velocity to be constant. Here in this case my axial velocity, that's what is varying. Now we need to do our calculation since we are having our axial velocity to be different. So we will do our calculation for different flow angles. So if we are putting our velocity triangle, so this is what is a triangle at the hub. We can say our CW2, it is nothing but B into RH. This B is our constant. That number we know it is 189.87 and hub radius is 0.1. So that's what is giving 18.98 meter per second. We can calculate our beta 1 since we know like my 10 beta, that's what is given by U divided by my CA value. So that's what it says, beta 1 it is coming 37.43. Okay. Same way at the exit also we can do our calculation for beta 2H. It is UH minus CW divided by CA at the hub. Be careful when you are doing your calculation. You must make a habit to write down what all data you know at particular station. Okay. Here our axial velocity, that's what is not constant. That axial velocity is reduced. So it is 32.83. So do this calculation carefully. It says my beta 2 at the hub, it is coming 10.61. Okay. So we can say we know what is our relative flow angles, relative air angles. Now at the hub we can calculate what is our delta beta. Since my beta 1 and beta 2 they are known to me. So we can say delta beta at the hub, it is coming 26.82. Just look at this number. Compared to what all methods you have solved where delta beta was coming to be different, here you are looking this number to be different. Okay. Now we can do our calculation for degree of reaction at the hub. This is what is the formula. Since my CA at hub it is known, so we can do this calculation. It says my degree of reaction, that's what is coming 0.62. Okay. Now we can do our calculation at, say, tip station in line to what we have done at the hub station. So that's what is, say, B into RT. That's what we are putting here. Okay. So we can calculate our CW2, we can calculate what is our beta 1, what is our beta 2 in line to what calculation we have done at, say, hub station as well as at the tip station. This is what will be my velocity triangle. Okay. Now based on this formulation we can calculate what will be our delta beta. So you can say my delta beta near this tip region, that's what is coming 33.95. Okay. And degree of reaction, that's what is coming 0.62. Okay, so this degree of reaction what we are calculating, that's what is coming to be constant at hub, mid and tip station. Okay. Now next parameter, that's what is very important here in this method. So we have seen our work, that's what is varying throughout my span, because that's what is changing with r square. So in order to take care of that, we need to calculate what will be my delta T0 at particular station. We need to check with what will be our delta P0. Okay, so here in this case, we know from our fundamental equation delta T0 at the hub, that's what is given by this formula. We are comparing our aerodynamic work and our thermodynamic work. So if we are putting this number, it says my delta T0 at the hub is coming 0.47 Kelvin. Okay. Now from our understanding of say our efficiency, we can do our calculation what will be my delta P0 at the hub. So if we are putting this number, it says at hub we are having our delta P0 to be 444 Pascal. Now look at and compare this with what all we have discussed up till now. For free vortex, what we have discussed, we are not having any variation of H0. If we look at for say our fundamental approach, where we are assuming this delta P0. Now for this force vortex method, applying force vortex concept, we are calculating what is our delta P0 at that particular station. Okay. Now similarly, we can do our calculation what is happening near the tip region. So it says delta T0 at the tip, it is coming 1.86 Kelvin, and my delta P0, that's what is coming 1783 Pascal. Okay, so this is what is a cross check kind of thing, how my delta P0, that's what is varying along my span. Okay, so if we will be putting this number, this is what is giving me the idea about the variation of different parameters from hub to tip. Say we will be taking these three stations. If we are comparing here, what we have done, we have opted for say force vortex concept, and because of say force vortex, we will be having our variation of CW2 based on our constant. Now because of variation of my CW2 and because of this force vortex, my axial velocity, that's what is going to change. At the same time, my number, that's what is C by U, that is also changing because my axial velocity at the hub is changing, my axial velocity at tip is changing. Okay, we can target our degree of reaction here. In this case, this is what is coming to be constant 0.62. We can say our relative velocity ratio is coming 0.80 and 0.66. If you look at carefully, my delta beta, what we are targeting near the hub, it is coming 26.82. That's what is very low compared to what all designs we have discussed up till now. But at the same time, that's what is say having slightly on higher side towards the tip region. We can say our degree of say diffusion factor, that's what is varying from 0.29 to 0.58. And here also, as we have discussed, our incidence angle, that's what we have assumed to be say positive 2 at the hub and negative 2 at say tip, and at the mid station we have taken that to be 0. Now this is what will give us the fundamental understanding in sense of how my flow parameter, that's what is varying at hub, mean and tip. Okay, here we need to be very careful with say use of the formula. Here we are not having flexibility what we were discussing in sense of our fundamental method. Okay, so whatever numbers, that's what is coming, that's what will be based on what equation you have selected with. Okay, so little careful and putting the equation in Excel sheet and finding these parameters. Now if we will be putting this, this is what is giving us in sense of variation throughout my span for 11 different stations. And here if you look at, this is what it says. If you look carefully, we will be having a gradual variation. That's what is happening for my axial velocity along my say radius. So you can see it is 32.83, and that's what is varying to 36.69 at the mid station and 41.49 near the tip region. Okay. Same way, this delta B beta, that's what we can see, that is also varying in a systematic way. Okay. So unlike what we have done for our say fundamental method, that's where delta P0, what we are assuming, we need to take care of how these flow angles are varying, how my delta beta, that's what is varying. Since this is what is say fixed with my radius, so we will not be having that much complexity in sense. But listen carefully, when we are using our fundamental method, we can decide which station we want to highly load or say low load. Okay, that's what is a great flexibility, that's what we are having. That flexibility we are not having for free vortex as well as for forced vortex design. Now you can see my degree of reaction, that's what is coming 0.62. We can say our relative velocity ratio, that's what is coming slightly lower near the tip region, and my diffusion factor, you can say it is 0.29, and my diffusion factor at the tip, that's what is coming to be slightly on higher side. So it is more tip loaded kind of configuration. Okay. Now this is what is very important. Once you are doing all this calculation, we have seen we can calculate what will be our delta T0 at the hub. We can calculate what will be our delta T0 at the tip. Based on that, you can calculate what will be my delta P0, and we can say my total pressure rise at the exit of my rotor, that's what we will be getting by averaging out along this span. And if you look at, we are expecting our pressure rise to be 1000 Pascal. Here this is what is coming 1045 Pascal. Okay, so this is also one of the cross check in that sense. You can verify this part. Okay, now this is how we are doing our design for the rotor. Now this is what, if you are doing carefully, if you are putting your formulation carefully, if you are doing your Excel sheet calculation carefully, this is what is the method, that's what will be giving us what we are looking for in sense of expected performance. Okay. Now in order to do the design for our say stator, we will be seeing here how we are looking at the variation of our angles. So here in this case, if you look at carefully, say this is what is representing my beta 1. Unlike earlier case where beta 1, that's what was coming to be constant because my CA and U for both the methods, that's what was same. Here in this case, since my CA, that's what is changing, and that's the reason why we are having this variation. So if you compare delta beta in this particular region at the hub and delta beta near the tip region, that's what is giving say not much variation. That means the blade what we will be making, it will be less twisted. Okay, so many times as per the requirement, maybe you are not looking for say highly twisted blade. This is what is the configuration, and if you compare, this is what is say higher diffusion factor near the tip region, and degree of reaction, that's what is coming to be constant. Okay, so this is what will give us idea in sense of how my variation of degree of reaction, my delta beta and diffusion factor, that's what is happening. We will see the comparison of all the three methods, that will give more clarity, more clear picture for the comparison part. Now in order to do the calculation for the stator, we can use the same approach what we have opted for earlier two methods, and there is no point in repeating the same steps here. You can see we are calculating our mid station. Okay, these are the mid station calculation. Now we are assuming our velocity, absolute velocity coming out from the rotor and absolute velocity entering inside my stator, that's what is to be same, and our exit, that's what we are assuming to be say axial. And under that configuration, if we are looking at, that's what will be giving me the variation of delta alpha. Okay, so here if you look at my diffusion factor, that's what is coming to be 0.23 near the hub region, and near the tip I am having this number to be 0.51. Okay, and degree of reaction, as we have discussed, this is nothing but 1 minus degree of reaction of my rotor, that's what is coming 0.38. Okay. Now just look at this part. So this is what is representing our blade when we are doing design using our force vortex concept. So if we look at carefully, the twist we were discussing, that's what is coming to be lower. Same way for hub also, we will not be having great turning, that's what is happening for the stator. So here near the hub region, my delta beta, that's what is coming to be lower. Even near the tip region also, we are not having this delta beta, that's what is coming to be large. Okay, so this is what is giving less twisted blade. Okay, and both of them, they are being stacked about the CG. Okay, let's look at what is happening in sense of when we are comparing these three methods. Okay, here in this case, if we look at, this is what is going idea about say fundamental method, free vortex method and force vortex method. Just look at, say this is what is representing my force vortex. So in sense of comparison, you can understand my delta beta, that's what is coming to be lower. Okay, so the twist for my blade, that's what will be lower when we are using our force vortex concept. For free vortex concept, we have realized near the hub region, we are having our delta beta, it's coming to be larger, and at the tip, that's what is say slightly lower, it gives large twist to your blade. Okay, same way here, if we are looking at say for fundamental approach, free vortex and force vortex approach, we will be having our stator that also is less twisted. Okay, let's see in sense of comparing all the three methods, what all we have discussed up till now. So here in this case, if you are looking at this green color, that's what is representing my force vortex approach. And if we compare, we have seen, suppose say this blue color one, that's what is representing my free vortex design concept, red color one, that's what is representing my fundamental method, and this is what is representing my say force vortex approach. And if we look at my delta beta here, that's what is not varying much from hub to tip. Okay, and you know my beta one, that's what is varying because my axial velocity is going to vary. Okay, now here in this case, if we are comparing say diffusion factor for both stator as well as for the rotor, we are having say diffusion factor to be slightly lower near the hub region, but it is higher towards the tip region. That's what is giving us idea about tip loaded kind of configuration. So when we are comparing say our fundamental method and force vortex method, my diffusion factor, that's what is coming to be lower. But at the same time, if we are comparing near the tip region, we are having this diffusion factor, it's nearby to what all we have discussed about the fundamental method. Okay. Now, if we are comparing what is happening with our say flow coefficient, as we have discussed, that's what is varying with variation of axial velocity. So near this region, if we are comparing, say this is what is representing what is happening with my loading. So this dotted line, if you are looking at, this is what is giving say constant kind of configuration. Okay, and if you are comparing our degree of reaction, you can say we have great variation of degree of reaction. That's what is happening for the free vortex near the hub region as well as near the tip region. when we are looking at say fundamental approach, for that my degree of reaction variation, that's what is coming to be slightly lower compared to free vortex approach. But for say this our force vortex approach, we can realize degree of reaction, that's what is coming to be constant. And this is what is representing what is happening with my de Holler's number. And if we are comparing this say relative velocity ratios, okay, for say our free vortex approach, this is what is showing a variation from hub to say our tip or say shroud. When we are comparing our case for say force vortex concept, that variation is not that drastic. Okay, we can see this is what is say nearly same kind of configuration we are getting in line to what we are discussing about say our fundamental method. So this is what is all, that's what is giving us idea about say comparison of these three design method. You can try with other design approaches also, okay, but we need to realize the thing is what you are doing, that's what should give what you are expected in sense of performance, in sense of pressure rise, in sense of efficiency, and later on we are also interested in what we say is in terms of say operating range. Now let me tell you, people, they are talking about different softwares which is taking care of optimization. Now you can understand, say you are optimizing by say different kind of approaches, what you are opting for, maybe that's what will be giving you what you are looking in sense of performance at one point. That's what is my design point. But it may be possible during off design condition it may go worst. So as and when you are doing your design, do that design carefully. Now we are having availability of open source softwares also. You can use open source software for say numerical simulation. You can check with what all we are discussing at this moment. You can compare your flow physics by these three methods. Now data sheet is with you. You are having say equations for making of aerofoil, that is also with you. So everything, that's what is now in open. So it's you who need to decide with what you will be doing with using this all data what we are sharing at this moment. So what all, that's what is available in open book. They are talking about design at the mid station and maybe talking design at say hub and tip. But you need to be careful and you must have realized it is not only that street station, that's what is very important. All the stations based on number of say equal division what you are making for span, they are important. Okay, so here we are stopping with today. We are going to stop our design for low speed axial flow compressor based on availability of data, maybe from research paper. You can start practicing. Now in sense of having say your examination, we will be giving some of the data, and based on that data you need to do calculation using say one of the method, and you need to share with what we say mid station calculation and your design Excel sheet. So thank you very much, and I hope you have enjoyed the design for low speed axial flow compressor. From next lecture we will start discussing about design of counter rotating fan. Thank you very much for your presence.